Greetings, physicists. This video is going to be purely about solving equations and doing math using algebra. And we're focusing on problems that involve constant acceleration. And really, in the physics that we're going to get to, this is about the upper end. We're not going to deal much, if at all, with changing accelerations or higher functions like jerk or things like that. So, let's get right into it. We got a lion. And lions are good sprinters, apparently. They have a pretty high acceleration, as you can see here. And he's going to try to catch this recreational runner who is running by at 10 miles per hour. So what we need to do, what I like to start with, is just, I'm going to find all of the given information. And when I say given information, I'm looking for a number and a unit to go with that number. So I read through, and actually my first given is not a number as you would think of one. It's this thing here, from rest. From being the key word there, although rest is also important. So I know this is a velocity. This is a velocity of 0. And the unit actually doesn't matter because 0 really is unitless, but we could say 0 meters per second. And because it's from rest, that's actually a velocity knot. So I'm going to go ahead and write that down as a given from this. Watch for those. Watch for clue words in your statements that can lead you to givens that don't look like givens the way we look for. All right, sustained acceleration of, oh, here we go. Here's another given, because this is easy to see. This is a number, 9.5 meters per second per second. There are two ways to write this. The problem has written it this way. I'm going to write it the other way. It says it's an acceleration, but even if you didn't know that, that unit is a clue that we have meters per second, and we're changing it every second. So this is an acceleration. And we're going to assume it's a constant acceleration. It says the line can sustain that acceleration. So we'll say this is a 9.5. The other way to write meters per second is meters per second squared. I would say, technically, that meters per second is more descriptive, is more correct. However, I will say that meters per second squared is almost universally used, probably just for ease, for the sake of easy algebra. But I would give the edge to meters per second from a technical standpoint, I suppose. Either way, you should get credit, no matter how you write yours. We'll keep going. Oh, for up to 1 second. That may or may not be useful. Yes, so it says the lion can maintain that for up to 1 second, but look at the question. The question says how much time. So we're actually looking for a time interval. So I'm not going to go ahead and write down that delta time is 1 second, mainly because delta time is what I'm looking for. So be careful with that one. The lion is capable for the 1 second, but the specific interval we are going to look at does not involve a 1 second time interval. How much time does it take a lion to go from rest, again from rest? Interesting. So my original from rest was technically not the one I was using, but it works out. How much time does it take a lion to go from rest to a typical recreational runner's top speed of 10 miles per hour. So if the starting speed of the lion is 0, the ending speed has to be at least 10 miles per hour for him to catch that runner. Or to equal that runner. I guess he'd have to go slightly faster. We'll go ahead and assume, though, that they mean they're asking how much time it takes to get to there. All right, so we have a V naught, we have a V, we have an A. Those are our givens, and we have an unknown. We have a how much time. So I'm looking for that. That's the question here. How much time? So the unknown is my delta time, is the interval. All right. Let's do some scrolling here. Now that I have all of this, nope, don't do that. There we go. So these are my givens. I have my givens. I have my unknown. I like to use the guess system. We have the givens. Check. We have the unknown. Check. We need to pick an equation. That's what that E stands for there. I have a bunch. I have an A. Excuse me. If you remember our kinematic equations, we have a delta x equals v plus v naught divided by 2 times a delta t. I should probably put the parentheses like this. Okay, so that's one equation. We have a v final velocity equal to a v initial velocity plus an constant acceleration times a delta t. We have a delta x is equal to initial velocity times the time interval plus half the constant acceleration times the time interval squared. And we have the final velocity squared should be equal to the initial velocity squared plus 2 times the constant acceleration times the delta x. And I can put lines over the a to make sure that we know those are constant or average accelerations. So let's look through my givens. I've got a v naught. Hang on. Let's see if I can draw. There you go. We got initial velocity, final velocity, acceleration, and time. Looking through my equations, I see this one has initial velocity, final velocity, acceleration, and time. So that's the equation I'm going for. That's how I'm going to figure this one out. All right, scrolling down here, I've got my equation now, check. I'm going to solve that equation algebraically for the variable that I'm looking for, which in this case is delta time. Delta time is my unknown. So algebraically speaking, if I take and subtract the v naught, I get v minus v naught equal to a delta t. And then I want to get the t by itself. I'm going to divide by the a and get delta t equal to v minus v naught over a. Okay, that's my solve step. Check. Now I got to substitute my things in. So if I go back, what are my values? They look like 0. Aha! I see a problem, or a potential problem, which is that my units for this velocity do not match either my units for my initial velocity or my units for acceleration. My acceleration is in meters and seconds, and my final velocity is in miles and hours. So I need to do some stoichiometry real quick. So let's go down here. I need to change 10 miles per hour into meters per second. So 10 miles over hours times. I'm going to have to get rid of miles and get meters. And I have to get rid of hours on top because hours were on bottom, and I have to turn them into seconds. I happen to know hours. 1 hour is 3,600 seconds. 1 mile is a certain amount of meters. I think it's like 621 meters. No, it's like 1.2 something here. Let's look that up. So if you don't know this stuff, that's all right. I obviously don't. Let's Google it. How many meters in a mile? And Google says it is 1609 meters. 1609 meters. So that will get my miles to cancel. It will get my hours to cancel. And I will be left with meters on top, seconds on bottom. So that is 16. Whoops. 1609 times 10 divided by 3,600. And I will get 4.469, or about 4.47. 4.47 meters per second is my final velocity, and that's going to go here. So let's plug, now that I have units that match, let's plug everything in. Delta time should be 4.47 meters per second is the final velocity minus 0 meters per second is the initial velocity divided by the acceleration, which was 9.5 meters per second squared. And sorry that my 5 looks like a 6. There you go. Okay, so let's take that and divide it. And I'm going to get an answer. So then the magnitude of my answer is just less than half a second. 0.47. Look at what cancels. I get meters that cancel. I get 1 of the seconds that cancel, and I'm left with 1 over seconds on bottom. So this unit is actually 1 over seconds. But if you fix that fraction, it's going to be 0.47 seconds. Good, we wanted a unit in seconds. So the time interval it takes the lion to get up to speed is just less than half a second, which if you're the runner trying to get out of his way is not very encouraging. That lion is gonna catch you. Cool. Let's go on to our next one. Drag racing. Okay, drag racer. Starts at rest, is going to travel a certain amount of space in a certain amount of time, and now we assume that this is just the first part of a larger time interval, and we ask how far will it go after the larger time interval. Okay, well, let's try this one here. So I'm gonna draw this for myself just so I can picture it. So here's my drag racer. Yes, very detailed drawing. And he starts from rest. Sweet. So right there at that starting line, or the starting line's front, either way. He travels for 1 second to here, and that is from 0 meters. Gosh, my writing is so bad. How do you deal? 0 meters to 6 meters, and then he keeps going and we also say that was from 0 seconds to 1 second, and he's going to keep going for an additional 4 seconds. And that additional is important because he's not going to end up at 4 seconds of time. He's going to end up at 5 seconds of time. He has to go 4 more seconds from that first interval. That's a key part of reading this. And we say at that point, at that additional 4 seconds, or at that 5 second mark, how far? So we're looking at what is his position? What is his final position? All right. Well, let's see about this. A couple ways you could tackle this problem. We definitely have some givens. We know that position initial is 0 meters. We know that position 1 is going to be 6 meters. We know that time initial is going to be 0 seconds. We know that time 1 is 1 second, and we are going to say time, we'll just call it time 5. It should be 5 seconds. That's not hard. And we're looking at what is x5 equal to. So we have our unknown. So these look like all the givens, definitely. And we're going to look for an unknown. Our unknown here is x5. So we have the g and the u. We need an equation here. I'm going to pick this equation. Because there's actually one more given that I didn't write down. Silly me. Because I even underlined it, but it was this one here, from rest. So velocity naught is 0 meters per second. And unlike the previous problem, all of my units agree with each other. Everything's in meters, everything's in seconds. So I don't have to do any conversions like I did last time. And so the equation I'm going to choose here that I like has to have x naught in it, has to have a time interval in it, has to have a v naught in it, and I'm going to go ahead and pick one and it has a constant acceleration. It doesn't tell us what that constant acceleration is, but this car continues this acceleration. So we know the acceleration is constant. So the equation I'm going to pick, which has all of those in it, is delta x equal to v naught delta t plus 1/2 a delta t squared. And I can do some things right away. A delta x is just an x minus an x naught, But notice our x naught is 0, so that's going to go away. So what I'm really going to get is an x out of this. A delta v, sorry, not a delta v, a v naught, right? That's also 0 up here. So I'm really going to get rid of that entire term. And so what I'm getting here is the x, whatever x we're trying to get to, should be equal to 1/2 of a times a time, or a delta time, squared. And the delta time squared is also interesting because delta time is time minus time naught squared, but time naught is also 0. So there are a lot of things that make this problem a little simpler. So I'm actually going to erase that delta because it's the delta time and the final time are the same in this case. So it's really just half of a times the final time squared, and the final time here is that we're interested in is 5 seconds. Now I want to make a point here. This half a is not changing. So we're going to do a little proportionality simplification here that's going to make this go a little easier. We could solve for a. We certainly have the starting interval. We could go from 0 to 1 and put the time in and get a. But this a is not changing. This is a constant a. So if you took x over t squared has to equal a for every x and t. So no matter what position you get to, if you got our initial, right, what we saw up here, we saw that x1 was 6 and t1 was 1. We know t5 is 5, and we're looking for x5, but the ratio of, let's go down here again, the ratio of, let's say, x1 to t1 squared is equal to a, but this should be true for any x. So if we did x5 to, or is half a, excuse me, x5 to t5 squared, that should also be equal to half a, because this is true for every x and t combination. So I'm going to set, if both of these are equal to half a, I'm going to set them equal to each other, and I'm just going to say x1 over t1 squared is equal to x5 over t5 squared. And then I don't even have to solve for my acceleration. It's right there. So that's my solve step. So I've done givens, unknown, equation. I've substituted. Oh, sorry, I've solved, and now I have to substitute. So x1 was 6 meters. It went 6 meters in that first interval. Divided by time 1 was 1, and 1 second, and we square it, so it's 1 second squared, equal to x5 is what we're looking for. I guess if I really wanted to solve this, I would multiply by t5 squared on both sides. And that will get the x5 by itself. So to get the x5, I have to multiply by t5 squared and cancel it off of this side. So t5 squared, t5 was 5 seconds. We went 5 seconds, so square that, and I'm going to get times 25 seconds squared. Well, the 1 doesn't make a difference. The second squared will cancel with the second squared, and I'm going to get 6 times 25. So that should be 150 meters is the leftover unit. That's how far I've gone after those 5 seconds. Cool. That's a standard proportionality, and that's something you definitely want to get good at. It will often save you time on tests. All right, going on to the next one. Okay, I guess we're down here. 3, let's look. A rocket sled accelerates. This is the next step up from a drag racer. This is how fast it accelerates. This is how long it accelerates. And we want to know how far does it go and how fast is it moving at the end of the interval. So let's write some things down. At 50 meters per second, so the acceleration, the constant acceleration, is 50 meters per second squared. For 5 seconds, that is a delta time. Not a starting or an ending. It says 4 or 5 seconds. So we'll do 5s here. what are the total distance traveled and the final velocity? I have an issue with this problem in that it does not state that it accelerates from rest. But I think in order to calculate the total distance traveled and the final velocity, we have to assume that it starts from rest. Poorly written problem, whoever wrote this. So V naught, I'm going to make an assumption, is equal to 0 meters per second. And I think that's the only assumption that can work in this case. We couldn't just assume that it started at, for instance, 1 meter per second. The problem would have to specify anything other than 0. All right. Accelerates at 5 meters per second for 5 seconds. Total distance traveled and final velocity. So I have two unknowns here. I'm looking for total distance, delta x, and I'm looking for final velocity, or v. And I can actually solve these in either order. I'll go ahead and solve for final velocity first because it requires a different equation. So I'm going to use this equation to get final velocity. I'm going to say v equals v naught plus a delta t. That should work because I have v naught a and delta t. And then for the other one, for the delta x, I should be able to do this one. I should say delta x equals v naught delta t plus 1/2 a delta time squared, like that. Because again, I have v naught delta t and a. So I can use those two equations. Interestingly enough, so I have my givens, my unknown, my equations, and I've technically already solved them because the unknowns are isolated, happen to be isolated in both of these equations. So that was a nice, easy fourth step that I didn't have to go through. All right, let's plug in for the first one. Let's sub. That's our last one. We have v equal to v naught, which is 0, plus a delta t, which is 50 meters per second squared, times a time of 5 seconds. And when I solve that one up, I'm going to get, well, 5 times 50 is 250. I have a meters per second squared times a seconds. I will lose a second and a second. There's 1 second on top and 2 on bottom. So what's left? Well, that's a meters per second. And that's exactly what I wanted because I'm looking for a velocity. So that makes sense to me. And it's a rocket sled, so it's going to be going fast. Okay, then I have a delta x. Let's do the second equation. Let's plug in for that. We have 0 is our meters per second times 5 seconds. Draw that 5 a little better. There we go. Plus half the acceleration of 50 meters per second squared times the time is 5 seconds squared. So I'm going to square that and get 25 seconds squared. All right, well, 0 times 5 seconds is nothing. Oh gosh, what's half of 50? Half of 50 is 25 times 25. So 25 squared, if you happen to have that one memorized, which I do, is 625. I have meters per second squared times second squared. There's second squared on top, second squared on bottom. That'll cancel, and I get 625 meters, which is good, because again, I'm looking for a distance. So this rocket that accelerates at 50 meters per second squared for 5 seconds will end up going 250 meters per second, and it will have traveled 625 meters by that point in time. Good to know. So not quite, a little over half a kilometer. On to the next one. Okay, another rocket, but it's a Saturn V rocket, so instead of shooting sideways, it's going to go upwards. Not quite as much acceleration. Of course, the Saturn V rocket, I would assume, is heavier and also is fighting gravity. But it goes up with a constant acceleration, and let's say, I think this is the same question, after 150 seconds, how fast and how far? So I think this is the same exact problem, but with different numbers. But let's make sure. It's launched, okay? And so, unlike the previous problem, you can pretty much assume that a rocket starts at rest if it's launched straight up. So we're going, yeah, we're going to do that. We're going to say v naught 0 meters per second. They give us a constant acceleration. That's 18. No apologies for bad penmanship. And we have a delta time equal to 150 seconds. Okay. Fast is it moving? How far has it traveled? So what is v final and what is distance? And again, I think we're going to use the same two equations as before. V final is equal to v naught plus a delta t, and delta x is v naught delta t plus 1/2 a delta t squared. And we'll plug some things in here. V naught again is 0, so I will just say that's 0 and not bother plugging it in, and I will say that term is going to be 0 and not plug it in. That'll save me some time. So my v final should be equal to the a, which is 18 meters over second squared, times the time of 150 seconds. I may have to calculate that one because it's just not coming up quick in my head. So 18 asterisk 150, and I get 2,700. Seconds cancel, or at least one of them does, and we get meters per second. So that's a fast moving rocket. All right, and we'll keep going down here. So my delta x, the distance it travels, will be, again, no initial velocity, so it's half at squared, or 1/2 of that 18 meters per second squared times, that's a big number, 150 seconds. I have to square that. I don't have that. Well, I might have 15 squared. I think 15 squared is 225, and 10 squared is 100, so you could just do 2,500 seconds squared. Yeah, I think that works. All right, so then I'm going to get half of 18 is 9. Seconds squared will cancel. I will get 9 times 22500. All right, let's see what that is. 9 22500. And I'm going to get 202,500 meters. So 200 kilometers in 150 seconds. Not bad. And reaching a final velocity of 2,700 meters per second. Sounds like a rocket to me. Again, this is very similar to the previous problem. Okay, let's see if we got a different one this time. We do. All right, fully loaded Boeing 747, full thrust. We're going to crank up all of its engines. Accelerates at 2. Look at that. Whoa, hey, that's not what I wanted. That's what I wanted. That's not as big an acceleration as I might expect for a plane. But again, if the rocket was 18, I suppose this is reasonable. It just seems like a small number. Actually pretty fast. Minimum takeoff speed is 70, so we've got to at least hit 70, or we're not getting off the tarmac. All right, how much time does that take, and how much space does that take? And this is really, if you're designing an airport, what you need to do. You take your biggest, heaviest plane, and you calculate how much space it needs to take off, and then you make the runway just a little bit longer than that in case something happens. All right, because I assume it takes more space to take off than to land. Well, let's go through and find some givens here. Again, we're taking off, so we are taking off from rest. That's not even given, is it? I'm looking through. I don't think it ever says it takes off from rest, but anyone so you have to bring that information with you, that airplanes take off from rest. V naught, 0 meters per second. We have an acceleration of 2.6 meters per second squared. And we have a V final. We have to get to that 70 meters per second, at least. So we're going to say our minimum V final is 70 meters per second. So this makes for a more interesting problem than well, not more interesting than the others, but at least it allows us to use a different equation. So I guess that's interesting. how much time does it take and how much length does it take? So again, two unknowns. I have how much time as an unknown, and I have how much distance as an unknown. So let's look through our equations. A time equation that works for this will be similar to the first problem we did, which was v equals v naught plus a delta t. That should be okay. But a distance equation is going to be the one we haven't used yet. So I'm going to use for my distance equation v squared equals v naught squared plus 2a delta x. And that will get me my delta x from the givens that I have above. Gosh, that a looks decrepit. I think drawing a circle with a tail would be easy. All right, so delta t first. Let's solve these equations for their respective variables. I'm solving for a delta t and I'm solving for a delta x. So the delta t will be equal to v minus v naught divided by a, if I'm doing my algebra correctly, and my delta x will be equal to v squared minus v naught squared over 2a. So that's my solve, and now I just need to substitute and chunk the numbers out. So here we go. What numbers do I have? I know v naught is 0, so that actually is going to be nothing in both of those, which makes this a little easier. So it's going to be v over a for there. And we know our top speed is 70, or our takeoff speed is 70 meters per second we got to get to. And the acceleration was the little bitty 2.6 meter per second squared. And that should get me my delta time. For my delta distance, that 70 is going to get squared, 70 meters per second squared over 2 times 2.6, or 5.2 meters per second squared. All right, I'm going to drag this, drag the whole thing over here, give us some space to work with here. Equals 70 divided by 2.6. Let's see what the calculator says. My calculator says 26.9, which I'm going to go ahead and round to 27. We have 2 sig figs, so 2 sig figs is good for this one. So 27. Units-wise, look what I got. I've got a meters canceling with a meters. I've got 1 second canceling with one of these seconds, and left over is 1 over 1 over seconds, or seconds. 27 seconds, which we were looking for, right? How long does it take to get up to speed? So if you've ever been in an airplane, 27 seconds, that's a decent chunk of time to get into the air for an airplane. Try counting it. It's more than, it feels like more. All right, let's do this one. 70 times 70 divided by 5.2. And I'm getting 942. If I want to round this the same way I rounded here, I rounded to 2 digits. This would be 940, because 942 rounds down, and which is fine. Again, 2 sig figs in each of these numbers, and we're multiplying, dividing. Now look what I've got here. If I square the top, I'm going to get, if I get rid of that squared, I'm going to get a meter squared over a seconds squared. So my seconds squared will cancel, but only one of my meters will cancel off the top, so I should be left with just meters, and that's what I wanted. I wanted a distance that it takes this plane to take off. So a Boeing 747, fully loaded, trying to take off, almost requires a kilometer-long runway. It's pretty close, and I'll bet you that if you look at the runways and measure them at a major airport, they're at least a kilometer long, if not longer, just in case. Yeah, because what if the wind's blowing in your face? Then you even have to go and account for that. So yeah, we got 27 seconds to get up to that speed, which is going to mean a 940 meter distance. Cool stuff. So we hit every single equation that involved acceleration. We didn't hit the constant velocity one, which was the x equal v plus v naught over 2 times delta t. That's okay. But hopefully this helps you out, and pretty much any equation or any algebra problem you encounter will involve one of those equations, or you could use you could use any combination of those equations to get to the right answer.